This is my presentation for the binary search tree project, the final. So first it runs an empty delete, so it deletes before any of this stuff's added. So then we add everything, we insert these, print and then print. Then we delete and leave, so the node with no children. Then we move down and delete a node with 1 child, and then node with 2 child. So that went all the way through, and then this prints the nodes and the time it took for that node. So 100 nodes, the binary search tree insert time, binary search tree delete time, AVL insert, AVL delete. So that's pretty much it for that. Next, most of the video will be in the code review. So we'll start with the AVL tree because this will be the longest or the largest file. So first we create the node class for the AVL, which uses everything from the node we made in the binary search tree, just the key and the value. And then this is the main difference in here is we're setting the height, which helps with balance and everything later on, and rotations and all that. So this is the actual class for the actual tree. So we initialize it, and we also use the binary search tree class also that we have in bst.py over here. So we initialize. This is the get height function. So it checks if there's nothing there. If there's nothing there, returns 0. Returns the height, which was 0, and then this is uses the get balance function, which is down here. Where's get balance at? I'm missing it. I'm missing it. Oh, define get balance right there. Getting the balance just takes the difference of the left node and the right node. And then the main difference between the AVL tree and the binary search tree that I found, the biggest difference at least, was the rotations that occur when balancing. It's basically just swapping the numbers around a parent node, just clockwise and counterclockwise for left. Then we have the insert, which really the recursive insert is what does all the work. So it checks if the spot's empty. If it's already empty, that's the easiest thing. It just exits there and creates the node there. This is the error case in case the duplicates. And then we'll go through the process calling the recursive insert to just basically recheck if the node is empty. And then continue to go through until it finds an empty spot. When it finds an empty spot, update the height of the node. Then we'll get balance of the node. Then we run all the balance to make sure that it's in the right position. And then we return it. And then the delete, just like the insert, the recursive delete is where it's really doing all the work. So this is, if there's nothing in the tree already, it just returns at the start. Check if the key is less than the node key, then go through and do the same thing with, it basically just does the same thing with each key until it finds the lessest key, and then it deletes it from there. So what's next? Yeah, that's pretty much all for the AVL tree. Yeah, like I said, the main difference between this and the BST, I think, is the rotations. So next we'll go over the BST, the binary search tree. Pretty much the same thing up here, and then this is the node class that we use in our AVL, which gives us a key value, left child, right child. These are optional using the type variable, so sometimes there might not be a child on the left or the right side. Then this is the class for the actual tree that will hold each node. Insert, just basically, again, same thing with the AVL tree. The recursive insert has a lot more, but if there's nothing in the spot already, it just inserts it there. If there's nothing in the root spot, so basically, if the tree is empty, it will insert it in the first place. And it moves down, then we do recursive insert, which basically just compares the current node to the key of the guy we're using until it finds the correct spot for it to get inserted into. Deletion, just like the AVL, it's recursively is where all the most of the work is. Yeah, check if the current node is none. If it's already empty, return. Then it just runs the normal comparisons again. And after it runs the comparisons, it just recursively runs the recursive delete on itself, through itself again, and again, and again, and again until it finds the delete spot. Yep, and then we move on to the next node. Next node. Then it runs recursive delete again. So it's basically just running it inside of itself until it finds the correct one it's supposed to be deleting. Then we have the find smallest function, which just goes through each node and compares them to each other and finds the smallest value. Then this maximum function finds like the highest, pretty much the opposite of the small, finds the highest key. So it goes through, compares, and then sets the maximum to what it is, which is maximum is usually the root. Then we have the traverse function, which is just records each node and adds it to the results list. And then we have the recursive traversal, which just does the same thing as this function, just recursively through each node in the list. And then we have the main. This is just the display. The display area for all of the insert times, delete times, calling the main functions and everything, all of our text and everything. So yeah, thank you.